then impairments are a completely different thing, right? Like the system itself has shape, and they are frequency related. So if you put a 750 megahertz passive in a system that's passing 1 gigahertz worth of traffic, you're obviously going to see that. But
Yeah, that
then
was
you
one of our
have
first problems is people putting wrong passives in and not changing them out when they try to upgrade to one gigahertz. And it turns out it's not the active, it's the passive you put into the active that's making it roll off.
Yeah, that's right. And we talked about on one of our amplifier videos about, not all passive plugins are created equal. They may look the same, the form factor is the same, and it may fit in the hole. But if you don't have the correct upper frequency band edge match to the device that you're putting it in there, you could be sticking a 750 pad and a 1.2 gigahertz amplifier and wondering where your high end went.
Someone uses a downstream equalizer in the upstream. It's not going to work very well.
So in addition to having the right passive plugins, and that's one of the reasons it's super important to look at your frequency response, not just a couple of channels to set up your amplifiers, because you may find things like that, the wrong passive plugin components, or even line passives that have been hanging in the plant for 20, 25 years, that don't have the same upper band edge or pass band that your system requires, not just because of impairments like these. But it is also important to note, if you're setting up your amplifier and you're not looking at your downstream frequencies, you may blast right past that suck out at 350 megahertz, right? You'll never see it because your high pilot channel or your OFDM channel or your low pilot channel aren't affected. And maybe on your the resonant peak there in the top left, maybe your high balancing channel at 625 megahertz is in that resonant peak. So you could be setting your tilt and your output of your amplifiers incorrectly if there happens to be one of these frequency response impairments in the channel that you're using.
Yeah,
So
I responded to one of your presentations earlier with you and Larry about, if I only relied on, and that's where I started with C-Core a long time ago, using a single level meter like a SAM or whatever to look at it might have been a Kalin at the time too. Remember the old Kalins? So we just looked at two carriers, and we never used channel 2 because it could be low and roll off. We might have used channel 5 or 6 or whatever, and they never used a very high end, but they weren't full of spectrum back then, so they might have put a pilot out there that was pretty stable, but you didn't know if it had high end roll off from water in a passive. So if you look at two channels that both had roll off, you could use a pad to pick those two channels back up, but then in the middle there was no problem, so you have this reverse bathtub effect and all this extra energy of all the other channels in the middle, when really you want to look at all the channels in relation to each other and make sure they're nice and flat or stable and not standing waves. And and also the point is, if you're relying on real channels and you have empty space, you can have a sweep trace that looks decent and then has this flat mark. Like, oh, it's nice and flat there. Oh, the only reason why it's flat there is because there's nothing, you're not looking at anything there. Right. You're connecting the dot from point A to point B, and you didn't put any sweep points in the middle. So right. Sometimes too good to be true is too good to be true.
That's fair. So these are all just different examples of downstream frequency response type of impairments that if you only looked at two tilt channels or a mini scan, you may not actually see the impact of the shape of the system. And that's what this really is the shape of the system. In this case, impairments is influencing the response of the signals, the desired signals, and turning them into an undesired shape as they travel through the impairment. So looking at the full downstream frequency response is super important when you're either setting up your amplifiers or just troubleshooting anything in general.
Yeah, even that bottom one looked like a impedance mismatch really far away, right? The standing wave looked really tight. So that bottom green one there, yeah. So it's a standing wave probably farther away, making a really tight standing wave. At least that's what it looks like from here.
Yep. All right, let's talk about the upstream. So we've blasted right past our 5 minutes. So we're just going to go with it. And similarly, the upstream portion of the plant has shape too. But where this gets really tricky for some people is that the modems in the customer premises have the ability to pre-distort their shape to counteract the effects of the shape of the system. So I put together, an example here of if we were to take and do an active sweep trace on the upstream, like we used to with the 3SR or the SDAs or the Kalins or whatever, you would determine that this is the shape of the cable or the network between the modem and the sweep receiver on the upstream for that particular 6.4 megahertz wide channel.
And more loss at the higher frequencies would mean it would drop more in the higher frequencies, right? So 542 or something like that.
Yeah, so this channel is up here around the diplex band edge of a subsplit system. And so what happens is the modem pre-distorts its shape to counteract, to exactly your point. This could be a diplex filter roll-off right here at 41.5 megahertz. So the modem can actually transmit a little bit louder in this portion of the channel to counteract the effect of that loss. So that when
this one channel, right? Because this is the in-channel frequency response. So it's an individual, probably 6.4 megahertz wide channel.
That's right.
I'm looking at your number there.
Yep, it's a 6.4 megahertz channel.
Or we're looking at your frequency in the middle, it's 29 to 41, so it's probably only 3.2 megahertz wide. You see
right, so you caught me, John. So this picture is a 3.2 megahertz wide channel. This picture is a 6.4 post equalized.
Hey, good enough. We get the idea.
Yeah. So the idea is the modem can pre-distort to counteract the effects of the shape of the cable response, so that when it receives the signal or it lands at the CMTS, that it's relatively flat.
Yep.
So if you put that all together, you can start to see some things and predict what is in front of a device. Now, this is an upstream modem traffic capture, right? So there's 5 upstream channels in this particular capture, and what's overlaid on top of it is the response of a high pass noise mitigation filter. So these are pretty common when we have ingress coming out of a customer's premise, to put one of these filters on the drop at the ground block or at the tap port to mitigate the ingress on the upstream. But those filters don't have super sharp edges. They're relatively low cost devices. And so they have what they call a filter skirt, or this leading edge that is not perfectly sharp. So what happens is the modem tries to talk through that. It recognizes that there's more loss at the leading edge of this channel than there is at the trailing edge. So your modem's in-channel frequency response may look something like this, where it's trying to transmit higher to overcome the loss on the leading edge of that filter. So that's a pre-distorted in-channel frequency response from a device that is trying to communicate through an upstream noise mitigation filter. Yeah, and then other things.
No, originally pre-EQ was never on by default, at least on the Cisco CMTS. So if you had a situation like that with that low end roll off of that upper fourth 6.4 megahertz channel, it might have an MER that could have been like 22 and 64 QAM wouldn't work. But pre-equalization, it has a lot of magic to it. It's able to pre-distort the signal, pre-equalize, and clean that up so that the CMTS sees a nice flat signal again, and the MER could go from 22 back to 30. So it's pretty impressive what pre-equalization was doing, not just in the frequency domain, but in the time domain as well, right? Group delay, timing issues that you don't see with the frequency response. So that roll-off usually also would cause group delay right there. And the pre-equalization takes care of the frequency and the timing aspect of that. So it's able to pre-distort the signal. And this is a whole premise behind, PNM, right? Proactive network maintenance is looking at this response from the modem to tell us what's going on in the plant.
Yeah, this is a very common one. So whenever I see a modem, particularly at a very specific frequency, it's easy to see that house has a filter on it. The other thing would be, the device is in a partially bonded state. It wouldn't be able to use the lower channels. So you can take a couple of those clues that you can get from PNM tools and say somebody likely installed a filter on that customer's device. The other ones are obviously loose connectors are just bad, right? We see a lot of in-channel frequency response problems just caused by loose connectors on the back of the modem. Very common one. The last one that I wanted to talk about was OFDMA. We talked about in a previous video the different evolution of DOCSIS and the introduction of OFDMA into the return. And what's great about those is with all of those OFDMA subcarriers, the resolution that we get from the in-channel frequency response of an OFDMA channel is really, really good, right? It's almost like having a sweep transmitter at the modem.
Yeah.
And then understanding what that's telling us about the shape of the system and the impairments in the system is really, really powerful.
I should use the term granularity, right? Resolution or granularity. It could be you have two options for OFDMA and downstream OFDM of 25 or 50 kilohertz subcarrier spacing. So in essence, if you did 25 kilohertz subcarrier spacing, you have a resolution of every 25 kilohertz. That's crazy, isn't it? The resolution you get with that. You could have a standing wave that's really, 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 really tight, which could show that you have a mismatch like 300, 400, 500 feet away, or a cavity in the plant creating a 500-foot cavity going back and forth, and everybody downstream of that that's going through that cavity would all show that same standing wave.
Yeah, and that's what I love about the OFDMA. Is just that resolution to your point, every 25 or 50 kilohertz, depending on how your upstream is configured, to really show you in fine detail the shape of your system. And I love this one because this is obviously a mid-split system. You can see this OFDMA channel goes from like 40 to 85 megahertz here. And this is effectively the shape of the system, and this is what you may see on your P&M tools. But the reality is you can see the loss at the diplex filter, right around that diplex filter cutoff region between 45 and 50 megahertz, and then that subsequent loss at the higher frequencies. So just understanding what ICFR is on the upstream in-channel frequency response and your frequency response on the downstream can tell you a lot about the shape of the cable and what potential impairments are out there that may be affecting your customer services. So just wanted to spend 5 minutes or less lull on what frequency response is, both in the upstream and the downstream, and how it can be used to help troubleshoot the network. So John, thank you very much for taking the time, as always, to share your expertise with me and with our audience.